I was just saying that we can have lots of different polynomials trying to approximate the same function. Here are graphs of Taylor polynomials trying to approximate the exponential function. In black, I've got the tangent line, and it turns out that the tangent line is just one of the Taylor polynomials. So it's special. We gave it a geometric sounding name at the beginning of this class, way back in Calculus 1. But it's just one out of a whole family. The way I like to think about this is, how did we build the tangent line? We built up the tangent line so it has the same value as the function, and it has the same derivative as the function, right? We needed that f prime. The second Taylor polynomial also uses the same, the second Taylor polynomial uses the second derivative of the function. So the second Taylor polynomial has the same concavity. The third Taylor polynomial will have the same third derivative. The fourth Taylor polynomial will have the same fourth derivative, and so on. These are the functions which match the derivatives of the function f at that centered value. So in this picture, they're all agreeing at x equals 0. So notice, here are those formulas for those functions. If I took successive derivatives of these things, I know that the first and second derivatives of this polynomial will match the first and second derivatives of the function e to the power x. And for that reason, this polynomial does a better job at approximating than the tangent line does. This cubic matches the 0th, first, second, and third derivatives of the function e to the x at coordinate x equals 0. And for that reason, it does a better job of estimating the exponential function than the second degree Taylor polynomial does. Now, granted, the exponential function will eventually grow faster than any polynomial, but as long as we're close to 0, we'll have a good approximation. If we want a good approximation somewhere else, then we would just center at a different value of a. Now, what do I mean by approximation? What do I mean by closeness? So what I can do to check whether or not the Taylor polynomials do a good job of approximating the function is I can just compute inputs and outputs. Here in this table, I've got the first handful of Taylor polynomials, degrees 2, 4, 6, 8, and 10. And I'm going to evaluate each of them at x coordinate 0.2 and see how good of an approximation that is. For x equals 2, all of these output values are very close together. They agree for a lot of decimal places, right? As soon as I get to T4 here, I've got my first 4 decimal places locked in, and then it's only a question of what comes afterwards. But if I try the same thing for x equals 3 instead, it takes me a longer time for those decimal values to get locked in, right? I don't even have the integer part of this number correct until my 8th Taylor polynomial. And even then, I'm not getting useful information. I would have to go further out and take higher degree Taylor polynomials. Well, why is this? Why should x equals 0.2 have a better approximation in this exponential function than x equals 3.0? Well, the reason is that I get a better approximation when I'm close to my centered value for the Taylor series. And this time I picked 0. My approximations get worse the farther away that I am from the centered value. And since 3 is farther away, I have a worse approximation. So this is something to keep to heart. If we want to approximate a function, we get better approximation or more accurate results from taking a higher degree Taylor polynomial. And we also get better approximation or more accurate results for using x values that are close to the centered value for the Taylor polynomials, for the Taylor series. So we have 2 different knobs we can move here for our approximation. We can try to take a very large degree polynomial to help describe a very complicated function. Or we can pick our centered value close to the numbers that we want to approximate. If I care about values of x close to 1,000,000, then I'm going to center my Taylor series at 1,000,000 instead of centering it at 0.